Here we have two vectors A and B whose tails coincide. The angle between them is theta. The dot product of them, written A dot B, is defined as the product of the magnitudes or moduli of the vectors by the cos of the angle between the vectors. Now you can see from this picture that if you multiply the magnitude of B by the cos of theta, then what you're actually doing is you're getting the length of the projection of B onto vector A. So imagine a line passing through vector A, and we drop a line from this point perpendicular to this line. So this red line is the magnitude of B multiplied by the cos of theta. So we saw this before when we were resolving a vector along a particular direction. But this is just the magnitude of this vector, and then we have to, well, this vector would be cos theta, so we're just dealing with the magnitude here, and then we'd have to multiply this by the magnitude of A to get the dot product. So we get the dot or scalar product. So this is a scalar, it's not a vector. Of course we could think of it this way. We could get the projection of A onto a line through B. So we take the tip of A, the head of A, project the right angles onto B, and the length of this line here, this red line, is A, is the magnitude of A, cos theta. So we just multiply this distance here by the magnitude of B to get the dot product. Now for the angle between the two vectors, we could use this other angle here, which is got from taking theta from 360 degrees. Now it's a fact that the cos of 360 minus theta is the same as cos theta, so it doesn't matter actually which angle you use. We know from trigonometry that if we have a point on the unit circle making angle theta with the positive x-axis, then the x value of it is cos theta. This angle here is 360 minus theta. Actually, I must measure from the positive x-axis, anti-clockwise. So, coordinates of a point on the unit circle are given by the cos of this angle and the sine of the angle. So, you can see that the x values of both of these points are the same. So cos theta equals cos 360 minus theta. And it doesn't matter actually whether theta is an acute angle or not. It's also true for any value of theta. So we don't have to worry about which angle we use when we're getting the dot product, because the cos will give us the same result. So that's A dot B. Now what about B dot A? Well, we get the modulus of the first vector, B, times the modulus of the second, A, times the cos of the angle in between them. Well, that angle is going to be the same as this angle here. The angle between A and B is obviously the same as the angle between B and A. But of course, the modulus of B times the modulus of A is the same as the modulus of A times the modulus of B. We're just multiplying scalars. So we see that the dot or scalar product is commutative. Here's a simple example. The magnitude or modulus of A is 6, the modulus of B is 7, and here's the dot product, 6 by 7 times the cos of the angle between them, which is 60 degrees. So the scalar product is 21. Now what about I dot I? Remember, I is a unit vector in the positive x direction. So we want the dot product of I with itself. So here's another I vector. Of course they're identical, so the angle between them is 0. If we join the tails together, the angle is theta is 0. So we're getting the cos of 0, which is 1. Now the magnitude of the unit vector I is 1. So we have 1 times 1 times 1, which is 1. And the same is true for j dot j. The magnitude of j is 1. This is a unit vector in the positive y direction. And the angle between j and itself is 0. Similarly for k dot k, where k is the unit vector in the positive z direction. Now what about I dot j? Well, these angles are perpendicular to each other, so the angle between them is 90 degrees. The magnitude of each of them is 1. So we've 1 by the cos of 90. Now the cos of 90 is 0. So if two vectors are perpendicular to each other, then the dot or scalar product is 0. That makes sense in terms of projection. If we try to project this vector or resolve it in the direction of I, we'll get 0. We project the tip of it onto I and join the tail to the tip, but we get 0. So here we summarize the dot products of unit vectors I, j and k. The dot product of a unit vector with itself is 1, but the dot product of a unit vector with one of the other two unit vectors is 0. So I, j and k are mutually perpendicular unit vectors. Now what about two vectors that have I and j components? So these are two vectors in the xy plane. So vector A is a1i plus a2j. Vector B is b1i plus b2j. Let's consider the dot product. Now, it turns out that the dot product is distributive over addition of vectors, something that we haven't proven. So we can take a1i and dot it into this vector here. So that's what we get here. Then we can take a2j and dot it into this vector, just like we would if we just had a multiplication sign here and we just had the sum of two real numbers here and the sum of another two real numbers here. Then we can dot this vector into this bracket here. So let's look at a1i dot b1i. Well, that's just the magnitude of a1i multiplied by the magnitude of b1i multiplied by the cos of the angle between these two vectors. Well, the angle between them is 0, of course. The cos of 0 is 1. These two vectors are both in the positive I direction. So here we just get a1. Now actually we have to be careful here, because the angle between the two vectors might not be 0. It could actually be 180 degrees. Like a1i could be pointing in the positive I direction, but b1i could be pointing in the negative I direction. That would happen if b1 is negative. Okay, if we multiply negative scalar by I, we get a vector pointing to the left. So the angle between these vectors then is got by putting the tails together, and we get 180 degrees. So we could have the cos of 180 degrees here, which is not 1 actually, it's minus 1. So the scalar product can be negative, but the way I was doing it, getting the magnitudes here, ensure that these would be positive, and then the cos of naught is 1. The whole thing would come out to be positive. Well, that depends. So a safer way to do this is to take the two scalars together, a1, b1, and then we have the dot product of the two i's. Well, we know that this thing here is 1. Okay, it's 1 times the cos of naught. So we get 1. Now if b1 is negative and a1 is positive, well then this is going to come out to be negative. So it will work out. But before I had this written down. And that looks like magnitude of a1 times magnitude of b1. Okay, if we ignore the i's. But this is always positive. We don't want that. It can be negative. The dot product can be negative. Next we have a1i times b2j. Well, we can take out the scalars a1, b2. I dot j we saw is 0 because these are perpendicular. Similarly over here we have a2j dot b1i, j dot i is 0, so we can forget about that term, that disappears. Then we have a2j dot b2j, j dot j is 1. So what do we end up with? We end up with a1 b1 plus a2 b2. These go out, these are 0. So now we have our rule. When we're getting the dot product of two vectors that are in the ij plane, we just multiply the I components together, that is a1 by b1, then multiply the j components together, a2 by b2, and add the result. So here's an example. To get the dot product of these two vectors, we multiply 7 by 5 to get 35, then plus 8 by minus 2 to get minus 16. So our answer is 19. We can extend that result to 3 dimensions quite easily if we actually go through it like we did the general case for 2 dimensions. you will end up getting this result here. Just multiply the I components, the j components, the k components, and add the result. So in this example here, to get a dot b, we multiply 5 by 8, plus 3 by minus 9, then minus 2 by plus 11. So we end up getting 40 minus 27 minus 22, which is minus 9. Here's another example. To get p dot q, we have 4 times 6, which is 24, minus 3 by minus 1, which is plus 3. 24 plus 3 is 27. Then we have 7 by 2 is 14. 27 plus 14 is 41. Now this one is a bit more interesting. We want the dot product of r with itself. So we multiply, we have r dotted with itself, so we have 3 by 3, which is 9, plus 2 by 2, that's 13, plus 9 by 9. So that's 13 plus 81 is 94. So r dot r is 94. Now we want to show that this is the same as the modulus of r squared. Well, to get the modulus of r, we use Pythagoras' theorem. We square the three components, sum them, and take the square root. And we can see that if we square the modulus, we get plus 94, the same as r dot r. So here's the summary of that result. The square of the modulus of a vector is the dot product of the vector with itself. So this is like projecting a vector onto itself. Get the projection of r onto r. Well, the length of that projection is just the modulus of r, and then we multiply by the modulus of r, the other vector, and of course we get this.